Hey, good morning. Good morning, Guru. Great having you for our next live stream today. We talk about re-ranking, but first I want to give you some really nice news. Google had an event yesterday, and they announced GPUs for Cloud Run. So if you're running machine learning workloads, now it's the time to switch them maybe over to Cloud Run. So we can scale down to 0. I think that's a great news. Check out the news. It's currently, you need to sign up first to get access to it, but documentation is already available. Really nice feature. That's very unique. Looking forward to that. All right, let's start with today's topic about ranking and re-ranking. Let's start maybe with something explainable. Imagine you're searching for an answer and you go to the library. Nowadays you probably use Google, but imagine you go to the library like we did years ago, and the librarian hands you a pile of books, but only a few pages are actually useful, right? That's frustrating, and that's where re-ranking comes in. It's like having this magic technology that puts the most relevant pages just on top. So you don't need to look through all the books. You get the most relevant pages right on top. And that's what ranking and re-ranking is about. Let's start with a ranker. I have this small image here. So a ranker is basically a language model that computes a relevance score using a document and a query. I think that's where it's actually interesting. We're using a document and a query itself. And the score computed here is high for a document with a contextual relevant query document pair, and low for the opposite. So if our question can be answered with this specific document, we get a very high score. If not, we get a low score. This is basically a ranker. We send a document and we send a query. And this score can be used to reorder documents and refine our top N further. Those ranker or re-ranker, we want to call them, they can be used standalone, but usually we kind of combine them with a vector search after the initial retrieval step. And we will discuss this a little bit later during the stream. TLDR for people who are short on time. So if you ask yourself, where's the difference between an embedding search or vector search and a ranker? The embedding search is usually about semantic similarity. So we have a document and we create an embedding. But we are missing this contextual similarity because we are not encoding the document with the query. We just take the document, create an encoding, an embedding, and store it in a vector database. So it's semantic similarity. Ranking is about the contextual similarity because we have the query and the document. I think that's the biggest difference if you want to take something with you out of this session today. Embedding, semantic similarity, ranking about contextual similarity. Guru is asking if there's a document or URL to this resource. I will publish an article as always, and there's everything in more detail, and we also write some code today, so we also have a GitHub repo later on. All right, re-ranking. I mentioned it. Re-ranking is about, or usually comes after the first stage of document retrieval. So it reorders the initial retrieved documents and improving the precision over the results. Let me open up a second screen. With a vector search, we usually retrieve candidates that are said already semantically similar to your search query. If that's your use case, that's good. But usually we want to use those candidates we retrieve from the vector search to answer questions. I think this process is particularly well known and important for retrieval augmented generation systems, where the relevance of the documents provided to the large language model directly impacts the quality of the generated output. And with a re-ranker, we kind of prioritize the most contextual and relevant documents and ensure we only provide the best information possible to your large language model. And this helps to reduce the context size because we don't need all of the documents, and it greatly helps to reduce the noise. And removing noise helps also to reduce hallucinations. So we get much better answers from our RAG when we have a ranking in place. This is obviously not true for all the cases, but we will see an example later. In practice, as I said, retrieval and ranking, they are usually combined. So the retrieval step is very efficient when working on a large amounts of data. You see it on the chart here. We have a lot of documents. We have a vector database. This is very efficient. We can retrieve a few hundred documents out of millions of documents very efficiently, which are semantically similar. And the goal of this initial step one, the retrieval step, is to have as many potential relevant documents as possible. Even if some of them might be not the perfect match, we still retrieve them. So the result, this results in a higher recall, so capturing more relevant documents, but also lower precision. So some of the retrieved documents might not be very relevant. The second step, you see on the right side, is the ranking step. This aims for higher precision. So the ranking step, the ranking API we're going to use today, ranks the retrieved documents from the vector search based on the relevance score, which we saw on the screen before. So about the contextual similarity. And the system scores and orders these documents, ensuring that the most relevant documents are the ones which are prioritized for the final output. And in this phase, we usually focus shifting from this refinement shifting to refining the results. So the system prioritizes the most relevant documents, which improves, as I said, the precision, ensuring the top results are highly relevant, but may lower the recall, meaning some less relevant documents are filtered out. And together, these two phases efficiently filter and prioritize information. So transforming this really large data set we might have stored in a vector database, a lot of millions of documents, into a very refined and highly relevant list of documents. So with ranking, if you want to put it into one sentence, with ranking, we remove irrelevant content or context from the large language model. Today we're going to use Google's ranking API. It's also known as Vertex AI Search Ranking API, Vertex AI Agent Builder Ranking API. There has to be too many renamings. I simply call it Google Ranking API. It's not the only one available. There are also ranking models from Cohere. There's Voyage AI, and there are also open source offerings on Hugging Face. The famous one is BGE Ranker, and there's also Mixspread on Hugging Face. So you can either use the APIs, Cohere is also really good, or you can use the open source models if there's a need for you. Let's go into the code. And I have this example prepared today. To use the Google's ranking API, we use the discovery engine, so it's not integrated into the Vertex SDK, as far as I know. I need to check that again. Or we can use the discovery agent, which is basically a wrapper on top of all the Google APIs. And we need a client for the ranking. There's a default ranking config, we need to have a project ID, and we can define a location. The standard stuff you can always do with those clients. And then it all starts with a rank request. So let me go down. You see this rank request, and this has a model name. In this case, there's just one model available at the moment. I'm not sure if there's planning to release more, or if maybe this stays the same. So it's called Semantic Ranker with a token length of 512 tokens. Well, this is already something we need to take into consideration. We are limited to 512 tokens of the content sending to the ranking API on the Google side. And then you can say how many of those top N documents you want to retrieve, depending on your specific requirements. Maybe you need 10, maybe just need 2, depending how granular you want to retrieve the reordered documents. And we are sending our query, our question, which we saw in the step before, and records. So our query would be, which language can I use for web development? And then we have a bunch of rank records. You see, we have a bunch of records. A rank record is basically just a document you want to rank. And because we want to rank multiple documents for this specific query, we have multiple ranking records. And a ranking record consists of an ID, which is your unique identifier, which you probably later on need again to retrieve the documents from a database, maybe. And then you can have an optional title and the content. There's no need to send the title, you can leave it empty, and the content of your document. This is what you retrieve from the vector search usually. right? You're getting content directly from your vector search and taking those maybe 50, 60, 100 documents and sending them to the ranking API. We can do that, and then we are sending the requests together with our query to the ranking API. We can give this a try. Let's go to the code. Run this, ranking.py. Oh, my video is stuck again. Nice. Thanks, Guru. Today it's not hot in the office, but let's see. So my video is working again. All right, you see we have this output here. Let me remove the side. And actually, let's have a look into the content first before we look at the output. So we see we have two contents about Python's programming language. So the first one and the last one. And we have something about the Python snake and something about Greek mythology. So the sentence 1 and sentence 4 are the most relevant to our question. And if we're looking at the results, we see it's now ranked. The sentence 4 has a score of 0.54, and then we have 0.37, and the other ones are lower. And you see, based on our query we had, so which language can I use for web development? Based on that, we're actually getting the first one as the best result. So we theoretically could skip the other steps or the other results and only keep the most relevant content, or you keep the top N. This is obviously a very small example. Usually we retrieve much more documents. So here we just have 4 available. But you see how the ranking works. This is actually a perfect fit for our question, right? This is what I mean with contextual similarity and not only semantically similarity, because we have query and the documents. And this is the difference between your embedding, actually, when you store the embeddings, and when you do this on a ranking time. For this test, we just had 4 very short sentences. Let's take this one step further. I have a few more or longer sentences, and we can also compare this to an embedding search to actually see how well is the pure embedding search compared to the ranking search, to see how well they behave, and if there is indeed an improvement over the questions and the documents. So let us open the other example. It's called ranking versus embedding. As I said, I put this all on GitHub. You can give this a try yourself. And you see I have a little bit more context now for these sentences. So longer text, but overall it's basically about the same topic. And I'm using, for this example, I'm using SQLite. They have this really nice SQLite vector extension nowadays. So you can use SQLite in memory vector store. Now also here with SQLite. You could also use Pinecone, Google's vector search. I'm just using this here because it's easy for me to give you an example without setting all the big infrastructure. And since we just have a few sentences, it works quite well with this approach. We set up the SQLite vector database. You see we are creating a vector table. You need to have the embedding length. So this is the default embedding length you're getting out of the embedding API. You can have longer embeddings or shorter embeddings, or you can configure it. This is what you get out of the Google embedding API out of the box. And then we are inserting them all into our vector database and running a small query. So we select the row ID and the distance from our vector items and embeddings where it matches, and order by distance, and I limit it to 5. You now have 4, that's fine. Could be also more. A little bit of boilerplate code to convert the distance into a similarity score. So usually you get something. When a document is a perfect match, you get usually 0, because it has no distance, right? It's the same document. But I want to convert this into similarity score, so we're getting something like a percentage. And then we're doing the same again. We initialize the ranking client service, same stuff we had before. I'm just now iterating over the ranking records and insert them into the discovery engine, into the ranking records. Same code here. Again, we have the semantic ranker and our records. I also measure the time, how long it takes to actually rank. Give you some insights into that later on during the live stream. And in the end, we have the ranking scores, and we also have the embedding scores, and we can plot them into a nice chart using matplotlib. So let's run this code. What was the name again? Ranking versus embedding. Let's run this. Takes a few seconds now, because we are first creating the embeddings, and then we insert them, and then we rank them. So you see it's now done. It took 500 milliseconds to rank those 4 records. That's it. We'll talk about latency in a second. But let's see how the result actually looks like. So it now generated this image here on the right side. We can open this up. And now you can see the sentences based on our query. The blue one is the embedding score we got out of the box. And you see that the sentence 1 and sentence 4, which are indeed about the Python programming language, they have a very similar embedding score. But if we compare that to the ranking score, you see the sentence 4 gets a much higher ranking score. So if you focus on a ranking, we could greatly improve this response, because sentence 1, it's about Python, but it's not related to our question. So we could remove those 2 sentences anyway, because it was about Greek mythology and something else. And we only keep the first one, which is highly relevant, and sending this to our large language model to actually answer our question. And by removing the sentence 1, which maybe contains also something about Python, we only keep the relevant context. And this helps to reduce hallucinations. This also helps to really have the model focus on what you actually asked for. So it will not return any information which is not relevant to a question. And you see how the ranking outperforms the embedding. As I said, it's a 2-step process, right? First, we usually do the embedding, the retrieval step, and then we do the ranking step. So they work in combination, they work nicely together. And if you just have a few documents, you could also use just ranking, but usually we have a few hundred, few thousand, even sometimes millions of documents. So there's usually a need for those initial retrieval steps after we do the ranking. All right, this is basically how ranking works. As I said, the Google semantic ranker model supports 512 tokens per record, including the title and the content combined. Anything longer will be truncated. And I think with this limitation, we need to also ensure when you are storing your documents in your vector database that you choose a chunking that fits to your ranking API or to your ranking model. Because if you store 1000 tokens in a vector database and then you do the ranking, you're going to miss those 500 tokens because they are truncated. So you always need to take the smallest limitation you have and apply this to your vector search as well. Also, one important point, a ranking request can contain up to 200 of those ranking records. So if you go here back, you see those ranking records, the documents we actually want to rank, you can rank up to 200 documents in one ranking session. If you want to rank more, you need to send multiple ranking requests sequentially or parallel, however you want to combine them. The latency, you see, we got 505 milliseconds. I also measured the average time it takes to rank a document. So I run a few examples multiple times, and it usually it's between it's around 500 milliseconds. But this heavily depends on correlates to the number of tokens you are sending to the ranking API. So the more tokens you have, the more time it takes to rank. So consider this as one of those things which you need to take into account, right? If you really aiming for low latency, you need to check if ranking actually adds too much overhead. And I think 500 milliseconds for those examples which we saw here. So it's actually not too short. We have quite some long text here, as you can see. I think that's fair enough. Pricing. There, we can actually open the pricing page. Always need to talk about pricing as well. So the pricing is $1 per 1,000 queries. What does query mean? One query can be up to 100 documents. So if you are ranking 200 documents, which is the limitation, you are getting billed for 2 queries. The price is comparable to other ranking APIs. The Cohere ranking API costs, I think it's $2 per 1,000 queries. So Google is $1 cheaper by the same number of documents per query. if you are using the open source model, it's up to your hosting costs, right? You could maybe host those models on Cloud Run. Now, if there are GPUs available, I need to do the calculation yourself, how much you actually pay. Let me also show you the Cohere re-ranking model. So here's the Cohere one. It's working the same. You're sending documents to the client, you define the ranking model, and you have your query. You see, it's exactly the same API like on the Google side, just the Cohere models. Which one to choose? Depends. There are benchmarks out there which test different large language models or embedding models, sorry, against different ranking models. So you need to find a good combination. You need to do evaluation yourself, depending on your specific use case, depending on what kind of model you use. Maybe a different ranking model provides better results, but it's something you need to evaluate and test yourself. As I said, there's also Voyage AI as a re-ranking model. And then we have the two most commonly used open source ranking models, which is from, I think it's from a Beijing academy. It's a BGE re-ranker. They're available in basic and small, as far as I know. And we have Mixspread. Those are the most commonly used. It's less downloads, so this is the most commonly used ones with over 500,000 downloads per month. So you can host them yourself if you would like to. As you see, it's very easy to use those re-ranking models if you want to put them in production. They are really low effort to implement and comparable low costs. So it can be a quick win for many of the projects. And what's also really cool and a nice tip, if you're using different data sources. So if you are getting, for example, results from a vector search, you're getting results from an API, results from a web search, and you want to combine those different retrieval sources, a ranker is perfect, right? How else would you do that? If you retrieve something from data source A, data source B, and data source C, put them all into the ranker, and then you can reorder the results from different sources. I think that's a extremely useful use case for re-ranker as well. So it's not only after the retrieval step of a vector search, you also can combine different sources. So if you ask me, should I use a ranker? The short answer is yes. Adding a ranker tends to lead to better results. I haven't seen a use case where the results actually got worse. It's either the same or better. And with those ranker models, we ensure that we only provide the best information to our large language model, which in the end enhances your model's response. And we all want to have the best results possible. Also, some people, they do those ranking with the large language model, right? They just send all the documents from the vector search to the large language model and let the large language model decide and extract the answer. But a ranker can be cheaper because you are reducing the context size. And this way, you're reducing your costs because you have less tokens. And depending on your model, it's also faster because the ranking model, they are quite efficient. And depending on your large language model, if it's a really big one, they are really slow. And especially if you have a large context, it makes sense to further, before we remove the context which is irrelevant, to make the ranker make the large language model as fast as possible. All right, so see, it's very easy to use. So give it a try. Later on today, probably I will publish an article with all the code, GitHub repo, and also all the charts and images you saw. So let me know how it goes. Ping me on LinkedIn and see you next week for a new live stream. We're probably going to talk about either context caching with Gemini, function calling with Gemini, or maybe even Cloud Run GPUs. So follow me on LinkedIn, YouTube, and don't miss the next one. And I wish you, again, as always, a wonderful weekend. See you soon. Bye-bye.